What is going on, guys? Welcome back. In this video today, we're going to take a look at Qdrant, which is a vector store, or we could also say vector search engine optimized for retrieval and also for metadata filtering. So the idea is, instead of just doing similarity search or semantic search in the vector space, we can combine this with filtering based on metadata. For example, keywords, thresholds, or similar things. Imagine the example that you have cars. You want to find the most similar car to a car that you provide. Let's say this is an image or text data, whatever. And then what you want to do is you also want to filter not just for similarity, but also for specific hard criteria, like give me the most similar car that has the same brand or the same color. So we're not just using these dimensions like color and brand in the vector space, we're also using them for hard filters that are coded in our script. So this is going to be a quick introduction. If you like this video, let me know by hitting a like button and subscribing. But now let us get right into it. Alright, so we're going to talk about Qdrant in this video today, which is, as I already mentioned in the introduction, a vector store with a strong focus on retrieval and specifically metadata filtering. So we can also have hard filters in combination with the basic similarity search. Now, I don't want to talk too much about this in theory. Let's get right into it. I'm going to go to my tutorial directory, which is my working directory, and in here I'm going to create a new project. Now, we're going to need a third-party package or a Python package, an external Python package called Qdrant client, in order to be able to work with Qdrant in Python. And you can either do that with your system Python installation. You can say pip or pip3 install Qdrant client like this. This is the most straightforward and basic way to do that. You can also create a virtual environment if you know how to do that. In my case, I'm going to do a UV project. So I'm going to use the UV package manager to say UV init and then UV add Qdrant client. The effect is the same. The only difference is I have an isolated environment. It doesn't mix across different projects. So I have here UV add Qdrant client is the same as saying pip or pip3 install Qdrant client, just that I'm doing it in this specific directory. And for now, that's going to be the only package that we install, because we're not going to actually use embeddings for the first example. I want to keep it very simple and explain to you how this works. And for this, I also want to open up my paint to briefly explain vector spaces. Now, we're not going to go into any mathematics here or into any very complex stuff, just so you have an understanding of what it means to use embedding models in vector stores. Now, in the context of RAG, oftentimes we want to find the most relevant piece of information. So we have some text, let's say, in the database, like some document here, and then I have some document here, and they have certain information. Maybe this is something about let's say C#, and then I have some code here about Python, just random examples right now. So I just have some stuff in the database, and this stuff can be in an ordinary SQL database. Now, sometimes what I want to do is I want to retrieve information. So I have an LLM, some AI model in the middle, and I ask it a question. Now, instead of just hallucinating or making up something that it doesn't know about, I want it to retrieve information from a database. Now, of course, it can do that with hard-coded queries from a SQLite database or from a Postgres database. But what I want to do is I want to find mathematically just the closest match to what I'm asking for. So for example, I could be asking for some Python code. And in this case, it should realize that this piece of information here is much more relevant than this one. So this one is not as relevant. I'm interested in this one. And I want to do that across many different categories, many different examples. I just want the AI model to be able to retrieve the most important, the most similar piece of information. That is what we use vector stores and embeddings for in RAG. And specifically how this works here, illustrated using just 2 dimensions, is that you have a number of dimensions. Usually this is not 2. This is something like 1,500 and something. Depending on the embedding model, you can have different dimensionality. But the idea is you have data points in this vector space. So maybe I have a point here, I have a point here, I have a point here, here, here. I have a bunch of different data points in this vector space. Now, this placement here is not random. If you have an intelligent embedding model, it's going to position these points depending on their semantic information. So depending on the meaning of their text. So for example, if this here is banana, so if this word here, I don't have a drawing tablet, so I'm just going to use my mouse here. If this here is banana, and this here is, let's say, kiwi or something like this, then this here could be apple. However, if I have something like computer here, this is PC, then this here could be Apple, but Apple in terms of company. So if I have a sentence, let's say, it's not just an individual word that I'm embedding, I have something like, I love Apple operating systems, then this Apple would be much closer to this data point, because we're talking about computers here, and here we're talking about fruit. Now, of course, 2 dimensions are not enough to properly place all the different things that we can place in such a vector space. That is why we use higher dimensional vector space. But the basic principle is you have different axes, different dimensions, and they have some sort of meaning. For example, we could have a male-female axis. If we say this is male, this is female, and then we could have something like very powerful and not so powerful. Let's say N for this. Then I could have something like very powerful up here would be king, for example. I could have king placed up here, and down here I would have queen. So they're both very powerful. So if that is the axis we're using here, they would be very powerful concepts, but they would have a different gender. That's like a very, very, very dumb explanation of what vector spaces are and how they work. Now, Qdrant is a vector store that can store these sort of embeddings, and then we can also do similarity search in Qdrant using these vectors, but we can also work with the metadata to enhance the filtering mechanism. All right, so let's open up the main py file, delete the default code if you're also using UV, and then we're going to code a very simple example. Now, the vectors we're going to use here are going to be handwritten, so they're not going to be actual embeddings, but we're just going to see how to work with Qdrant if we have some vectors, and we're also going to play around a little bit with the distance measures. So for this, I'm going to start by saying from Qdrant client import Qdrant client. So that is going to be the class. And also we're going to import a couple of models. So we're going to say from Qdrant client.models, we're going to import vector parameters. This is going to be important for the size, so the dimensionality of the vector space, and also for the distance measure. We're also going to need distance for the distance measure, obviously, and also point struct for the actual individual data points. So point struct is going to allow us to create objects that we can then feed into the vector store, or as it's called here, upsert into the vector store. So after the imports, we're going to just say client is equal to Qdrant client. And as I said, we can either specify a host or we can specify a path on disk. I'm going to go with path here to keep it simple. I'm just going to say this is going to be in the same directory, vector underscore store. Now, one thing, since I don't want to do fancy if statements here, for the sake of simplicity, every time I start the script, I'm going to delete that directory. So this is just so I can run the same script multiple times without having to encounter a message like this vector store already exists. I'm just going to delete it every time and run everything from scratch every time we run the script. For this, I'm going to import shutil. And I'm going to say shutil.rmtree and vector store. Like this. This just deletes the directory and everything that is in that directory. So after that, we can create in this vector store that we automatically create by just referencing it. So it either loads the vector store if it exists, or it creates a new one. And in this vector store now, we want to create a collection. A collection, you could say, is like a separate database or a separate section in this vector store. So for this, I'm going to say client.createCollection, and we're going to provide a collection name. This can be whatever you want. I'm going to just call mine first underscore collection. Now, the second keyword argument here is vectors config, and vectors config will be where we pass our vector parameters. So I'm going to say is equal to vector parameters. And in here, I'm going to specify the size. So the dimensionality of the vector space. In my case, I'm going to go with 2, the very simple 2-dimensional example that I showed you in my paint. And I'm also going to say that the distance measure is equal to distance dot, and we're going to start with the basic Euclidean distance. So for those of you who don't know what the Euclidean distance is, it's basically the distance of the Pythagorean theorem. So you have 2 points, and it's just instead of going left and or right and up, you just go the diagonal. This is the Euclidean distance. So we have our collection now, and into this collection, I want to upsert some data points. So I'm going to say client dot upsert, which is basically the same as insert. And we're going to still target the collection name here. So I'm going to have to specify again first collection. Then I'm also going to say weight is equal to true. And then I can provide my data points. So I can say here points is equal to, and then a list of point structs, which is just individual data points in this vector space. So I'm going to say point struct, then I need to provide an ID for every single data point. For the sake of simplicity, for this first run, I'm just going to provide 1, 2, 3, 4. Later on, we're going to use UUIDs. So for now, I'm just going to say ID is equal to 1. Then the vector itself, so the data that we're trying to, or the position of this point in the vector store needs to be specified. In our case, we're going to just provide 2 values since we have a 2-dimensional vector store here. And I'm going to do something basic like 0.1 for the x coordinate, 0.1 for the y coordinate. So for the first dimension and the second dimension. Now, in addition to that, and this is now interesting, we can provide a payload. So I can say that the payload for this specific point struct is that it has a certain role, and this role could be boss, for example. So this is a people database, we could say, and one of those people at position 0.1, 0.1 has the role boss. Now I can copy this and do it 3 more times. I can say ID is equal to 2, 3, and 4, and I can adjust some of the coordinates. So for example, here I could say negative 0.1, 0.1 could be worker. And then maybe if I want to go with something like 5, 5, that could be king, for example. And then something like 2020 could be God, which is of course completely random and stupid what I'm doing right now, but I just have some data points which I myself as the intelligent embedding model now placed here, and they now live in the vector space. So maybe just to visualize this, what this would mean is that we have this 2-dimensional vector space again, and then I have one point which is kind of here, let's say, or actually even closer to the origin. Then we have one point that is kind of here, then we have one that is kind of here, and one that is maybe here. So that would be the God point, this would be the king point, the boss, and then the worker. So what you can see is that these 3 here are basically all lined up in the same direction. They have different magnitude. If you consider them as vectors, they have a different magnitude, but they have the same direction. Whereas this one goes into another direction. Now, depending on the distance measure, you will get different similarity values now. So if I want to know, for example, the similarity between this new embedding here and all the other ones, it depends on the distance measure. Now, in the case of the Euclidean distance, I just go the direct path to these data points. That is going to be the similarity. So the further away you are from this point, the less similar you are. The closer you are to this point, the more similar you are. However, this is not the only distance measure that we can have. We can also have something like the dot product. And in the case of the dot product, this one here would actually be quite similar to this one because magnitude is like an amplifier. So in the case of a dot product, the 2 points that are the furthest apart are not necessarily the least similar. And then also you have something like the cosine similarity where all of these would be equally similar to the other point because they're all in the same direction, and magnitude is irrelevant in terms of the cosine similarity. So we're not going to get too much into the mathematics here, but you need to understand Euclidean distance is a basic distance measure useful for clustering. The dot product may be more useful if you do something like a recommender system where you have preferences for a certain genre, and then if that genre is present in some data point in some movie, for example, with a very high magnitude, that would amplify this and make it more similar, even though the arrow would be further apart from your point. And then something like the cosine similarity makes sense for recommendation systems because you basically only care about the direction of the vector, not the magnitude. But that's too much talk again. Let us go back into coding. Let's say here we want to have results of a query comparison or of a similarity search. I'm going to say results is equal to client.query. Or actually, the method is called query points. And here now I'm going to provide a vector that I want to use as the search query. So I'm going to say query is equal to, and then let's say we have negative 0.08 and 0.9. So very much in the direction of worker, not so much in the direction of, or actually not 0.9, 0.09 is what I wanted to say. Very much into the direction of the worker, not so much into the direction of the other 3. And depending on the distance measure, we're going to get different results here. So if that is my query, I still have to pass here the collection name, which is going to be the same as above, first collection. And then I can also specify whether I want to also get the payload in the result. I'm going to say yes, I do want to have the payload as well. And then finally, I can say limit, give me the top 5 results. In this case, of course, we only have 4, so we're going to get all of them. But this is like a top K result set. And what I want to get from all of this is dot points, so the actual data points. Then I can just print results. So that is the most basic example that we can have. We can say UV run main py. If you're not using UV, you can just say Python main py or Python 3 main py. And it says now no such file or directory vector store, of course, because it only works if the directory exists. So for the first time, I'm going to comment this one out. And now it works. You can see we get scored point, then another scored point. These are basically the results. And for my provided instance, let's say this was clerk because it was quite similar to worker. You can see the Euclidean distance here gives me this as a score. So this is basically the distance score, which is very small because it's very close to the data point, which is why this is the first hit that I get. then I get boss, then I get king, then I get god. God is very far away from clerk. Now I can also change that and say that I want to use the dot product. Just by replacing this with dot, I can now use the remove command here. And in this case, you can see that the closest match is God, because God has a very large magnitude, and this is what makes it very attractive. It leads to a very high dot product in this case, because they do have a similar direction to some degree, and God has a very large magnitude, so it hits here as being the top score. And then finally, I can also go and do cosine similarity here as a distance measure. In this case, I would get still like worker as the closest match here, but also you can see that for the other three, I get the exact same score because they're all in a line, they're all pointing to the same direction. Now, let's take this and actually work with real embeddings from real embedding models. For this, what I'm gonna do is I'm gonna add two packages. One is going to be OpenAI, the other one is going to be python-.env. OpenAI is going to be used to interact with the OpenAI API, so we can use an embedding model from OpenAI. You can also choose a different one. You can also use a local one if you have one. And python.env is going to be used to load the API key from a .env file. So I'm going to install these two packages. Again, you can do Python, or actually not Python, sorry, pip or pip3 install, and then OpenAI or python.env as well. And then you want to create a file called .env, like this, .env. Now, in my case, I already have this file, and it already contains my API key, so I'm not going to show that, but I'm going to create another one here and show you what it looks like. You basically say OpenAI _API _key, then you paste your API key from the OpenAI platform, then you close that file, you save it, and it's automatically going to be loaded by the python.env module as long as you call it .env, not .env.test. This was just to show you an empty file. You want to call it .env. Then we can go into main py. We can start by saying from OpenAI import OpenAI, and then also from .env import load.env. And then we want to call load.env. This is going to load the API key into the environment, so OpenAI already recognizes it immediately. Now, we're going to keep the rest the same here for the most part. We're going to change a couple of things. I'm going to rename first collection here to languages. So I'm going to say replace first collection. Do that with the editor of your choice. I'm going to call this one now languages. So that's just going to be a renaming of the collection, nothing fancy. And I'm also going to create an OpenAI client. So I'm going to say OpenAI _client is equal to OpenAI, and that's basically it. Now, instead of just adding any random points here, I'm going to use programming languages. So these are not going to be full text. You can also embed full text. You can also embed images depending on the model that you're using. We're just going to take individual names of programming languages and we're going to try to find the most similar ones. And for this, the first thing we need to change is we need to change the dimensionality of the vector store, because the embedding model that we're going to use from OpenAI produces embeddings with a dimensionality of 1536. So that is the number. This is the dimensionality of our vector store. This means we have that many different directions that we can move into, this many different floating point values per embedding. So we also need to set up the database to reflect that. Then below the OpenAI client, I'm going to insert two lists. I didn't want to type them out myself. These are just strings. We have interpreted languages, compiled languages. That's basically it. We have Python, JavaScript, Ruby, PHP, Perl, and then C, C++, Rust, and so on. So we have two different types of languages. The reason I'm showing you this is to show you how the filtering works. But I also want to show you how to do that with OpenAI, so how to actually get the embeddings for these specific terms. So right now we just have the strings. So what I'm going to do now is I'm going to say interpreted embeddings is going to be equal to, and we're going to do a list comprehension. We're going to do it one by one, even though you can also do that in a batch. I just want to show you the basic principle. OpenAI client.embeddings.create. Then we specify the input. The input is going to be the string. So in our case, we're going to call that lang for language, because we're going to do a for lang in interpreted languages. And the model in this case is going to be the text-embedding-3-small. So this is going to use the embedding model here from OpenAI to embed the text of language. This is going to be an element of this list here. And then from the result, I want to get data, and I want to get index 0, and I want to get from this result the embedding. And all of this has to be done for every language in interpreted languages. That is the line of code here. Now I can copy that and I can adjust that to also work for compiled languages. So compiled embeddings are going to be equal to the exact same thing. The only difference here is we're going to do that for compiled languages. And then we can basically do an upsert or two upserts in this case for these embeddings. And we can also specify the type of language in the payload so that we can also filter, hard filter by type, by compiled or interpreted, not just on the embedding level, not just trusting the embedding model to do the right embedding, but to actually be able to force a filtering to exclude all interpreted languages, for example. So here for the points, I'm going to say the points are going to be the following list. Now I'm going to import UUID to not have to specify IDs manually. So I'm going to say points is equal to a list where we have point struct. The ID is going to be UUID4, just some random identifier. The vector is going to be equal to interpreted embeddings I, so index I. And then we're going to say that we want to have a payload. So maybe let's do that in a more structured way here. Let's say ID vector like this. And then we want to also say payload is equal to a dictionary, and this dictionary should have on the one hand the language itself, which is going to be interpreted languages I, and also I want to have the type. In this case, all of these are going to be interpreted. And I want to have such a point struct for every single data point. So for I in range, length, interpreted, embeddings. Then we can copy this and we can just replace the word interpreted by compiled. So I can say interpreted, compiled, and then it works for that as well. Now, the final thing that we need to change here is the query. We cannot just provide a two-dimensional vector here. What I'm going to do is I'm going to say query embedding is going to also be OpenAI client dot embeddings dot create. Input is going to be equal to some programming language. So if we look at this, we don't have C#, for example. So I can go and say I'm interested in the closest matches to C#. And then I'm going to say again, model is equal to text embedding 3 small. From that, I want to get again data index 0 embedding. Now replace the query with the query embedding here. And that's basically it. So this is without any filtering yet. This is just getting the closest matches. So I can say UV run main py now. And you can see the results say that the closest match to C# is C++, followed by C, followed by JavaScript, followed by, what do I get here, PHP, and then Lua. I don't know if I agree with that, but right now this is what the model gives me. Now let's say I want to do the similarity search, but I want to make sure that all the languages that I get are interpreted. I don't want to say, give me the most similar compiled languages. I want to say, give me the most similar interpreted languages. Or also, I don't want to say like, give me just the most similar languages, give me the most similar interpreted languages. So I want to make that filter specifically, not in a fuzzy way, not in an LLM instruction kind of way, but as a hard filter. In this case, what I can do is I can go back into my main py script and I can say from Qdrant client dot, or actually I don't have to do the import again. I can just continue here. From Qdrant client models, I also want to import filter, field condition, and match value. So these three can be used in combination to create a filter that is a field condition that has to be an exact match to a value. So all I have to do now is, in addition to the querying down here, I can specify the filter. So I can say query filter is equal to, and then I can create a new filter instance. This filter will have a field condition. So I'm going to say must is equal to, because we can also have like optional fields, but we can say must. What has to be the case is there's going to be a field condition, and this field condition is going to be targeting the key of the payload type. I can also do that for any other data that I pass here. I can also say something like inventor or year that this language was released or something. But now I'm going to just filter for key type, and the match has to be the following. It has to be a match value where the value is equal to interpreted. So the syntax is not the most straightforward one. It can be a bit confusing, but essentially what we're doing now is we're doing the exact same thing, but we're forcing all of the resulting languages to be of type interpreted. We don't have any compiled languages. So now if I run this again, we can see that I still get 5 results. I get JavaScript first now, no C, no C++, I get PHP, I get Lua, I get MATLAB, and I get Perl. So that is what Qdrant is all about. This is a very, very minimalistic example. We can do much more filtering here, but that is what we can do. We can combine metadata filtering with similarity search in a vector store. Now, let me briefly show you that we can also do the same thing with Docker. For this, we only have to go into our script and change the location of this vector store. So let me remove the shutil. And here we're not going to say path, we're going to say host. And in our case here, that's going to be localhost, and the port of Qdrant is going to be 6333 as a number, not as a string. So that is the same code, the same functionality, but now we're doing this with a Docker container. Now for this to work, of course, we need to have a Docker container running with Qdrant. So I need to say here docker run. I'm going to map the port 6333 to 6333. Then also 6334 to 6334. I'm going to create a volume, which is going to be current directory, so pwd /Qdrant storage, just so I can persist the data. So that is going to be mapped to in the container Qdrant, and then storage. And the image is Qdrant /Qdrant. So this is just an image that is available. Okay, I already had an instance running. I needed to stop that, but now I can run this. This opens up Qdrant locally, and now I can do the same thing as before. I can say uv run main py, and you can see stuff is happening here on the right side, and the same thing works as well. So you can either do that with a Docker container, or you can also deploy this somewhere on an actual web server and use it there, or you can use it on your file system. Now, finally, I briefly want to show you a practical use case of this. I have a side project on GitHub, which is openly available. You can take a look at the source code called Latent Assets, which is just a very small little project I started some weeks ago. Basically, what you can do here is you can run, you also have the README commands here, you can run the embedding server, the backend and the frontend. This combines image embeddings with text embeddings, and you have like a vector store where you can look for images using text. You do a semantic search using text to find images. So here now I started the embedding server, the backend and the frontend. Then I can open this up in the browser, and this is just a simple tool where I can drop some images in here. So for example, I uploaded now 6 images, and what I can do here is I can basically just upload them. They're automatically going to be recognized. Now these are all thumbnails, of course, but I can also provide tags. For example, I can say this is a hardware video, and then this is a tag, and then I could say something like this is AI stuff, this is agentic stuff, whatever. I can provide tags. I can also provide multiple tags like AI here, and I can then upload these images to my vector store. And then they're uploaded and added to the vector store, and then I can search for them. So for example, I can do something like Python. So I can search for Python. I will get the top 5 matches for this. This is some other image that I recently had in another example, but now I have like these results based on a similarity search. However, since I provided some tags, I can also provide AI as a query, search, and then if there is an exact match with a tag, I will get this image first. So in this case, you can see I get AI model quantization and agent skills here as tagged. These are first results because I have some metadata in here that allows me to find them with a hard filter. So why is that interesting? The interesting thing is that we're using Qdrant to do that. So these are just the experiments, but if I go into latent assets, backends, then I can go into vector store, and you can see how all of this works. So this is not super crazy or anything, but we have basically a query mechanism that uses also the hard filter. So we can actually say here that first of all, we want to look for the filter. Query filter is tag filter, and tag filter is a filter with a must condition, field condition, key equals tags, has to have the value in there. If that's the case, we're going to get it definitely in the result set. And if we don't have enough results, then we're going to do another query here without any filter. So that's just a very simple example on how you can use that. But essentially, Qdrant is what you want to be using if you're focusing heavily on retrieval and metadata filtering. Now, people will say, what about PG Vector? Why should I not just use PG Vector for everything? You can use PG Vector. It has some benefits. You're using just one database for everything. You just have an additional column. It is it is easier to handle, but I would say that if you're focusing on performance, if you're focusing on scalability, and your application heavily revolves around retrieval, RAG, and also metadata filtering, Qdrant is probably the better choice. If you have a very versatile application, you just have one side feature, secondary feature that involves RAG, I would use PG Vector. But if you have an application that's heavily focused on retrieval, Qdrant is probably the better choice here. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested, on my website, you will find a services tab and a tutoring tab. There you can contact me if you need help with a project, if you need a freelancer, if you need some advice, some consulting, or if you want one-on-one tutoring, me teaching you a concept one-on-one, you can contact me there at the bottom of the pages via LinkedIn or via email. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and